Okay, so we're a couple 2 minutes early, but maybe we can start slowly. So indeed, our group is called Nonlinear Algebra. And nonlinear algebra is a friendly way of saying algebraic geometry. So algebraic geometry to some people sounds a little scary, a hardcore topic in theoretical mathematics. But in some sense, it's the next step after linear algebra, viewed from the outside world, from a light topic. So there's this book with Mateusz Michalek that serves as a basic reference. So whenever I say algebra words like tensor, tensor rank, prime ideal, Gröbner basis, so I'll say these kind of words throughout the lectures. This would be a basic reference. So the 6-week program is about amplitudes and algebraic geometry. So my perspective on algebraic geometry is it's the study of zeros of polynomials. And I mean it, okay? I really mean it. So for me, algebraic geometry is zeros of polynomials in several variables. And such a zero set is called a variety. And a variety, just like Sandra, generally walks into the room. And so there's a variety. And the first question we would ask this variety, what is your dimension? How many degrees of freedom do you have, right? And the second question we might ask is, what is your degree? How curvy are you? But then we're also very interested in the polynomials that describe this variety. So this will be a recurring theme in these lectures. So the way the lectures are organized is sort of the opposite from most other lectures. So most sane and reasonable lecturers like Melissa, they will build up slowly, right? So the first lecture will be very understandable, and then it gets harder, and then maybe by lecture 3 or 4 you possibly get lost. But in the beginning, things are easy. So my lecture is the opposite. So number 1 is the hardest, right? And then it gets easier, progressively easier, and then lecture 4 will be the easiest. So what this means, even if you're not here right now, you can come tomorrow, or you can come back on Thursday. So they will be completely independent, and I would say today might be the hardest. What I like to do in this lecture, I like to tell you about varieties that are described by variables. Hi, Marvin. And these variables have these funny names. They're called like bracket ij here in blue, or maybe here in red. So this is the goal. So I encountered varieties described by polynomials and some variables, and these variables have these funny names, and I like to tell you about these names. So this lecture is based on 2 recent papers. So for the most part, I'll talk about material in this paper called Kinematic Varieties for Massless Particles. So this is a work with 2 PhD students at Berkeley, Swala Sverresdottir and Smita Rajan. And then towards the end, I'll make a little bit of advertising about another paper called Spinor Helicity Varieties with Yassine El-Mazouz and Anna Al-Fister. And this was published in a journal that we like. So in my community in applied algebraic geometry, we like the SIAM journal on applied algebra and geometry. So the way we got into this is I wanted to understand the mathematics behind Smita's bachelor thesis. So Smita wrote a bachelor thesis in physics at Brown University with Anastasia Volovich, whom the Amplitudes people in the room know. And I want to understand what's in her master's thesis, right? Because she was interested in working with me, and that led to this paper. So I'm sorry, her bachelor thesis. And this bachelor thesis also then became part of this article called 5-Dimensional Spinor Helicity for All Masses and Spinors that was published in this journal. And this journal, the Journal of High Energy Physics, is the most popular journal for people who work on scattering amplitudes. And so we're going to jump between things you might read in this journal and things that you might read in this journal. So in the meantime, Smita has taken a turn towards a really theoretical algebraic geometry. So she's co-advised with Hannah Larson, sort of a Berkeley algebraic geometer. And so she came from physics and now is doing sort of hardcore algebraic geometry. Okay, we're going to work in a d-dimensional real or complex vector space, RD or CD. And we're going to talk about particles in d-dimensional space-time. So the worlds around us, usually d is 4, right? So we have 3 space dimensions and 1 time dimension, but we're also interested in higher dimensional situations. Here, these authors were particularly interested in d equals 5, and we're going to allow arbitrary d. So on this vector space, we're going to fix the Lorentzian inner product, right? So this n is a d. I think Christian just found this. So the dot product in this inner product between 2 vectors x and y is almost the usual dot product, except we start with plus, minus, minus, minus. So this is signature 1, d minus 1, and then this n is a typo that should be a d. So the group of d by d invertible matrices that leaves this inner product invariant, that's the Lorentz group, SO1 d minus 1. So this consists of d by d matrices with determinant 1 that fixes this inner product. So for the usual signature, this is just the usual rotation matrices, but the 1 d minus 1 indicates that we have this different signature. Now with the complex numbers, in principle it doesn't matter, right? Because over the complex number, any 2 inner products are equivalent. And if you're willing to write down things like the square root of minus 1, you can change between any 2 non-degenerate inner products. But over the real numbers, this makes a difference. And in physics, it's very common to work with this inner product. So now we're going to look at a configuration of n particles. And each particle, the ith particle, is given by its momentum vector, pi. So this is a vector with coordinates pi1 up to pid. So we're going to represent a particle, whatever that is, by such a vector. We're going to talk about n particles in d-dimensional space. And please interrupt me with questions, right? So as always, especially when teaching calculus, right? So if you don't have questions for me, I will have questions for you. Please ask me questions. So there are 2 basic assumptions that we're going to work with in this lecture. So we're going to assume that each particle is massless. And massless means that the inner product of pi with itself is 0. Okay? Now for the usual dot product over the real numbers, this equation doesn't have a lot of solutions. But of course, with this inner product, there are lots of solutions. And so the real solutions to these equations are vectors that lie on the boundary of the light cone. So the light cone is given over the real numbers by requiring that this expression is non-negative. You are supposed to stay inside the light cone, right? That's the universal speed limit. You're not supposed to go outside. And if you're on the boundary, then you are a massless particle. And we're going to assume that this equation holds for all I, from 1 up to n. Now, furthermore, we're going to assume that momentum, yes? Okay, very good. So the question is real versus complex. So maybe another word of philosophy in applied algebraic geometry. So of course, often in applied algebraic geometry, we deal with data science and optimization and biology and the rest of it. And then we're really interested in real numbers, often non-negative real numbers, or maybe non-negative real numbers in a box. Okay? So then we're going to describe some situation with polynomial equations, and it's very difficult to make any kind of statement over the real numbers if you have equations and inequalities. So then what we're going to do, we're going to make our problem easier in 3 steps. The first step, we're going to throw away all inequalities. We only look at equations. Now that makes our problem easier. Okay? The second thing we're going to do is we're going to replace the real numbers by complex numbers. Now that makes the problem much easier because now polynomials in one variable always have the right number of roots. So we simply pass to the algebraic closure to make whatever problem we have easier. And the third step is we're going to replace affine space by projective space. Any two lines in the plate meet in a point. Okay? So now we are in complex projective space, and now the problem is so easy that even algebraic geometers like Marvin and me might be able to say something. Okay? So the general philosophy is we're sort of trying to formulate things in a complex projective space with the understanding that ultimately we might want to go back and address harder questions over the real numbers. And in lecture 3, I'll talk quite a bit about real numbers. Okay? So today, varieties for the most part will be complex projective varieties because it's easier to work in complex projective space. All right. So this is the title. Ideals, Variety, and Algorithms is the title of a popular undergraduate textbook in algebraic geometry. And here's what we do. So a new variety comes along, right? So let's write IDN for the ideal generated by the equations on the previous slide. So we form a polynomial ring in n times d variables. So that the entries Pij. So that's the jth coordinate of the ith momentum vector. And we're going to look at the ideal generated by the n quadrics for massless and the d linear forms for momentum conservation. So these are the quadratic equations. So think about a n by d matrix of variables. The column sums are all 0, and every row satisfies the same quadratic equation. I throw these into an ideal. Let's try this for n equals d equals 3. So we have 3 particles on the boundary of this ice cream cone. Okay, so we go to our favorite computer algebra system, right? So if you're a physicist, that would be Mathematica. If you're a German computer algebra person, that would be Oscar. And in my community for a long time, that would be Macaulay too. So we form a polynomial ring in these 9 variables over the rational numbers. So here's one more important thing that I need to say about applied algebraic geometry. The zeros, the varieties that we think of, is over the complex numbers. The calculation that we do is over the rational numbers. Right? So we're going to do rational arithmetic. We're going to add and multiply rational numbers. Right? You can never see a complex number or a real number, right? Before you see a real number, you are dead, okay? So I want to do these things while I'm alive. That's why I'm working over a computable field. And for me, a computable field is the rational numbers, and Matthias Aschenbrenner in the back knows many more computable fields. Right? But for me, this is the rational numbers. Okay, so let's try it, right? So we type in our equations, so these 3 linear equations, momentum conservation along the columns, then the quadratic equations along the row. So then we're going to ask for the dimension around the codimension. So the codimension in this 9-dimensional space is 6. So this is a 3-dimensional affine variety. That was the first question. Second question, what is your degree? How curvy are you? And the degree is 8. So this is a 3-dimensional variety of degree 8. If you paid attention, this follows for Bézout's theorem. Okay, then let's ask some other questions. Is this ideal a prime ideal? And the answer is no. This is not a prime ideal. This ideal does not suffice to represent all polynomials that vanish on this variety. Right? So prime ideal means very good ideal. In the olden days, I would say like prime rib or prime time. Nowadays, I would maybe say Amazon Prime. Okay, so prime means very good. An ideal is prime means it's complete. It's all the polynomials that you need. And if you want to look up, as I said, adjectives like this, the yellow nonlinear algebra book has them all. But then you ask, are you primary? Are you a scheme that's supported on this irreducible variety? And the answer is yes. Well, whenever this comes back, maybe the next question you would ask is you compute the radical. This is a typo, this should be just I. And then the radical reveals that there are additional equations that vanish on the variety that are not yet generated by the ideal. Okay, so this is the very first thing that anybody would do, when this variety comes along. Okay, so this is a primary ideal, but not a prime ideal. However, as soon as n and d are at least 4, then it's actually a prime. Okay, so this was an exceptional case. So the case where d and n were 3 was exceptional, but there's a little theorem that says that this ideal is a prime ideal, and it's a complete intersection. That means the codimension is the number of equations. So the number of equations agrees with the codimension. That's very, 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 very special. So in algebraic geometry, usually varieties are not complete intersections. Usually varieties have many, many more equations than the codimension. The codimension is always bounded above by the number of equations. That's Kroll's principal ideal theorem. But it's rarely the case that they agree, and if they do, that's a complete intersection, and that is the case. And the proof is actually quite technical commutative algebra. All right. Now, another thing that you might ask for, is there a parametric representation of this variety? What do I mean by this? So, parametric representation means that you have a map, a polynomial map, from some other space into your target space, and the variety you're studying is the closure of the image. Now, going from a parametric representation to the implicit representation, that's called implicitization, and that you can always do in principle. So if you have a parametrized variety, you can compute the implicit equations, that is to say the prime ideal, by elimination, and that's a standard task explained, for example, in the elementary undergraduate textbook with this blue title. But what's more interesting is, can we go back? If you're given a variety, can you find a rational or polynomial parametrization? Now here the story is very interesting. Okay. So most varieties cannot be parametrized in this sense. Elliptic curves, most plane curves, if you are a smooth plane curve of degree 3 or more, you do not admit such a parametrization. So it depends whom you ask. So if you ask an official algebraic geometer, such as Balázs back there, are most varieties rational? Can they be or unirational? Can they be parametrized? The answer is no. Right? So most varieties that you would see in theoretical mathematics do not have such a parametrization. On the other hand, if you look in the real world, if you think about statistics, data science, biology, and all that, most varieties that you see in practice do have such a parametrization. And the reason is because varieties arising in applications often describe some generative process, some kind of statistical or physical process that generates points, and it's this process that furnishes the parametrization. There's a dichotomy. So in theoretical mathematics, varieties typically do not have a rational parametrization. In applied math, in the sciences, they usually do. Physics is in between. Okay, that makes it very interesting. Okay, so is there a parametric representation? Well, the most naive thing to do is, well, you have a bunch of equations. The first batch is all linear. Those you can solve by hand, right? And then maybe you can also work on the columns. So the first idea is to express the variables in the first row and column in terms of the complementary n-1 times d-1 matrix. Right? You like the idea is you sort of eliminate the first row, you eliminate the last column, and voila, you have a parametrization. Turns out that doesn't work. So it turns out if you carry out this elimination, then you're still down to a hypersurface. It's an irreducible polynomial of very large degree, 2 to the n-1. And this hypersurface is a notable obstruction to an easy parametrization. There is no easy parametrization. So for example, if you're in the world around, if we're in d equals 5 with 4 particles, this is a complicated irreducible polynomial of degree 8 with 4,671 terms, and I don't know how to write down a parametrization. Okay. Yes, Balash. Oh, the given generators are, so the given generators generate the prime ideal. So the theorem is that these blue things and these blue things generate the prime ideal and they are complete intersection. If d and n are at least 4. It's the right number. So there are n equations here, there are d equations there. So it's n plus d, and that's the right number. Okay, that's it. So what you see is what you get. That is. Okay, now what I'm saying here, it's not easy to see a parametrization. And in fact, that is precisely what physics teaches us. So the physicists call this make this membership manifest. So one of the favorite adjectives in physics is manifest. In fact, it's a verb in physics. And to manifest the rationality of this variety is what we have all these complicated spinor brackets that we're going to see. So there is a way to do this, but it requires coordinate transformations that are not easy, and for mathematicians, for algebraists, quite counterintuitive. Okay. That was the warm-up. That was the first 5 pages. Okay, now let's progressively get to better coordinate systems. Now, geometry, according to Felix Klein, is invariant theory. Right? So properties that are geometric are those that are invariant under the relevant group, and the same is true in physics. So a quantity is physical if it has necessary condition, has to be invariant under the appropriate group. So the group here is the orthogonal group or the special orthogonal group. So let's look at the ring of G invariants. So this group acts on our polynomial ring by acting separately on each row, right? It moves around our points. And the ring of invariance, according to Hermann-Weyl, so a classical result due to Hermann-Weyl from the 1930s, says that the pairwise inner products Pi dot Pj generate the ring of invariance. And we're going to abbreviate this by Sij. So Sij is the dot product between Pi and Pj in the Lorentzian inner product. That's how kinematics enters. So when Lorenzo later talks about Feynman integrals, whatever particles he's going to smash together, they will be represented by Mandelstam invariance. Sij is the inner product. Okay, so algebraically speaking, we're looking at our polynomial ring, modulo our ideal. This quotient is an integral domain. And we take the ring of invariance, and then the ring of invariance is the polynomial ring in these variables Sij modulo a certain ideal. That and we're going to call this the Mandelstam ideal, and the corresponding variety we're going to call the Mandelstam variety. So in algebra language, the Mandelstam variety as an affine variety is the spectrum of the invariant ring, or we take the previous happy complete intersection variety, and we take the quotient modulo the orthogonal group. This is the GIT quotient, the geometric invariant theory quotient. Pardon me? MDN is the ideal. Okay, so MDN is whatever relations the Sij satisfy. Okay, so these are, so Sij, now notice that Sii is 0. That clear, right? Because Pi dot Pi is 0. That's stipulated by this ideal. So we have n choose 2 of these Sijs. Sii is 0. So these are the entries of a symmetric n by n matrix whose diagonal is 0. And there's some obvious relations. For example, this matrix has to have rank D. This matrix, both physicists and mathematicians alike call this a Gram matrix, and this Gram matrix has its d+1 minors vanish. And that's going to be pretty much this idea. All right, now there it is, spelled out. So now here d is at least 4 and n is at least 2. Then this prime ideal, okay, it's again prime. And prime is an adjective you should know. And prime is even better than prime. Primary is pretty good, but prime is even better, okay? And then this prime ideal, of course, as I said, the diagonal entries are all 0. The row sums of this matrix are now 0. That comes from the p's. And there's a rank constraint, so this Gram matrix, Sij, has its d+1 minors vanish, so the d+1 minors are elements in this prime ideal. The Mandelstam variety just walked into the door. So this is named after Stanley Mandelstam from the 1950s, and I'll tell you more about him in the third lecture. And first question we always ask, what is your dimension? How many degrees of freedom do you have? Well, this is the number of original matrix entries, n times d, minus n for the rows, minus d for the columns, minus the dimension of the orthogonal group. So this is the expected dimension. And this is what you would expect in a quotient situation. It's the dimension of the previous variety minus the dimension of the orthogonal group. All right. We reached slide 6. And this was the easy warm-up. So this was supposed to be very easy for the mathematicians in the room, maybe a little bit puzzling, new words like primary for the physicists, but this would be a very good moment to ask a question. Because from now on, it's going to get harder. Okay? And I told you this is the hardest lecture of the 4. Lizzie. Yes. I'm going to make it projective as the talk goes on, just to make it a bit more friendly, but yes, they're really projective. All the equations are homogeneous equations. Yes, Claire. Okay, well, the ideal is the algebraic relations of Sij. So what you do is you make a polynomial. You go to Macaulay 2. Or Oscar, or mathematics. You make a polynomial ring over QQ, over the rational numbers, because you can never see a complex number while you're alive, okay? You start with the rational numbers, you make variables S12 up to S blah blah, then you write down a second ring, you make the polynomial ring in P, so you have the S ring and the P ring. Then you write down that Sij is equal to Pi1 times Pj1 minus Pi2 times Pi2 minus P1, and so on. You write that all down. And then you say kernel. Right? You have a ring map from the S polynomial ring to the P polynomial ring. The ring map is given by the assignments I just sang for you. And then you say kernel. And then the kernel comes back. And that's NDN. Clear? So that's what we do. Right? All right, so this was the easy part of the lecture. Okay, so now buckle your seatbelt. Yes. Well, it's an equational description. So is there a parametric representation? Yes, there is, and I'll tell you later. Right? That's what's called making something manifest in physics, to give a unirational representation, but it's not obvious, right? It's not obvious, because of this little tiny thing that the diagonals are 0, it's not obvious how you should parametrize this. And we're going to parametrize this as the hour goes on by some weird variables called spinor helicity variables. These are 0. So this describes n by n symmetric matrices of rank at most d whose diagonal entries are 0. Elia, question, comment, complaint. Oh, what's the spectrum? Very good. So a ring has a spectrum, and again, this is in the nonlinear algebra book. So if you have a variety, it has a coordinate ring. So this is the ring of functions or polynomial functions on this variety. But you can go back, right? So if you have a ring, you can make a variety, and in an algebraic geometry course, that's called the spectrum. And officially, the spectrum is the set of all prime ideals with the Zariski topology, but it's just the algebraic geometer's way of saying, I'm going from the ring to the space, to the variety. And Hannah will be happy to tell you more. That's what they study in a math course. I forgot, Oxford or Cambridge or something, Imperial. All right, okay. Clifford algebras, okay? So, what was the goal of the lecture? The goal of the lecture was to tell you about these brackets. What are these brackets? And as we go along, this will represent something called spinors, and to talk about spinors, we need Clifford algebras. And here are the references. So kinematic data for n particles are often expressed in terms of spinors. Here's one textbook that I've spent some struggling time with by Elwang and Wang called Scattering Amplitudes in Gauge Theory and Gravity. I found this article quite useful in learning about Clifford algebras in this context. There's an article called Clifford Algebras in Physics, and I had never studied this. I don't know about the other algebraists here, but I had never studied Clifford algebras. I don't know. Melissa, when you're a student at Berkeley, did you? Okay. So we didn't study, Clifford algebra. So what's a Clifford algebra? A Clifford algebra is the following. Let's start with a finite dimensional vector space over a field, not characteristic to. Okay, so let's start with the finite dimensional vector space, and then let's form the free associative algebra. And also this vector space comes with the quadratic form. So the vector space together with the quadratic form, like our R to the n or R to the d with this Lorentzian inner product. Okay. Now this is the tensor algebra, or the non-commutative polynomial ring, the free associative algebra. And what you do is you define the Clifford algebra as follows. You mod out by all relations v tensor v minus qv, where little v, right, ranges over all vectors in the vector space. You take any vector in the vector space, think of it as a linear form, right? Take the non-commutative product, right, this v tensor v, and then you subtract the value of the quadratic form, that's a scalar, times 1. And then you take all of these things, you form the two-sided ideal, and that's your algebra. Okay? That's called the Clifford algebra of a vector space together with the quadratic form. Now, a good example to think about is the quadratic form 0. So if the quadratic form is all 0, and that's the exterior algebra. So if you have the quadratic form and it's all 0, right? So if you take the free associative algebra mod everything of the form v tensor v, right? Then you get a finite dimensional vector space of dimension 2 to the n, n is n 2 to the d in my notation, and that's the so-called exterior algebra. And so this is a deformation of the exterior algebra. So every quadratic form that's non-zero deforms the exterior algebra to another algebra called Clifford algebra. And Melissa and I had never seen this in our study, but physicists are very familiar. But to get some street credit among mathematicians, you need a math reference. And I found this book by Chevalier, right? So the algebraic theory of spinors and Clifford algebras. And mathematicians, of course, like Bourbaki. So here's the reference that gives this some street credit among pure math people. Okay? So those are Clifford algebras. So let's jump in. So in the physics way of describing, now we're going to talk about the Clifford algebra. This is the Clifford algebra for our vector space with our Lorentzian inner product. sometimes called the Dirac-Fermi algebra. All right. So for us, spinors are going to be vectors of length 2 to the k, typically column vectors, and k is d over 2, rounded down if d is odd. Okay. So now we're going to describe certain matrices, and those are going to be 2 to the k by 2 to the k matrices, and we're going to find d of them, right? So now we have a d-dimensional vector space. So just to make clear, right? So this vector space here is maybe c to the d, and this Clifford algebra is some 2 to the d-dimensional algebra. Okay, so when are we going to do this with k, which is d over 2? Okay, so if d is 2, then k is 2, right? And maybe I made this already oh yeah, no, that's okay. So if d is 2, then k is 1, and then 2 to the 1 is 2. Okay, so gamma 1 is this matrix, and gamma 2 is this matrix. Okay, now we're going to make larger matrices. So for larger even integer d, we're going to take tensor products with so-called Pauli matrices. So this little thing, and this little thing, I here is the square root of minus 1. So these things are called Pauli matrices. So they generate the Lie algebra of SU2. So these are 2 by 2 Hermitian matrices. And okay, then, each time you form a tensor product, the size multiplies by 2. So this makes matrices of size 2 to the k by 2 to the k. Now, if d is odd, well, you have to do this a little bit differently. You take the remaining odd indexed matrix, you multiply everybody else except for the last one, and you multiply by a power of I. So now I've defined for you d big square matrices. Now these big square matrices, they form a representation of our Clifford algebra. Right? So these Dirac matrices form a representation of the Clifford algebra, and what I'm going to do is I'm going to take Q to be 2 times Lorentzian inner product. So just for technical reasons, I take the inner product where the diagonal entries are minus 2, 2, 2, 2, 2. Okay, so this big matrix, gamma 1, if you square that matrix, you get negative 2 times the big identity matrix. Every other big matrix, if you square it, you get 2 times the identity matrix. And then every anti-commutator, if I and j is not the same, is a big zero matrix. So this means these matrices, when you multiply them, satisfy the defining relations of the Clifford algebra. So they satisfy the relations stipulated in this two-sided ideal, so they are a representation of the Clifford algebra. Good. That has, let's do one more further. So now how we're going to sneak in, momenta. So now one particle comes along. A single particle comes along, and it has a momentum vector with coordinates p1, p2, up to pd. And we're going to encode this harmless tiny little particle in a very big matrix, namely the corresponding linear combination of these Dirac matrices. So on the previous slide, we introduced defined big square matrices, gamma 1 up to gamma d. And now we're just going to take a linear combination, and here we have a minus plus plus, just like in the signature. Okay, so let's do an example. So if d is 4, then k is 2, and 2 to the k is 4, right? So here is the momentum space Dirac matrix, and the coefficient of p1 is the first Dirac matrix, the coefficient of p2 is the second Dirac matrix, and so on. And so this thing is called the momentum space Dirac matrix, just a general linear combination of our d big square matrices. Okay, then if d is 5, well, k is still 2. The matrix is almost the same, except you put a p5 along the diagonal like this. Okay, then for d equals 6, so if d is 6, k is 3, 2 to the 3 is 8. So our big matrices are 8 by 8 matrices. So Claudia, there are 6 8 by 8 matrices, one for each coordinate of the momentum vector, and I'm packaging them like this. Okay? So notice this is a block matrix, and it's neither symmetric nor skew symmetric. It would like to be symmetric or skew symmetric, but it isn't quite. But it has these blocks. Okay? So this is just a way of packaging all these matrices, gamma 1, gamma 2, up to gamma d, the matrices that I defined on the previous slide by tensoring together harmless little Pauli matrices. Gamma, where are we? Gamma? First line. Oh, yes, sorry, I should have defined this. This is recursive. So I'm defining gamma I for k in terms of the previous gamma I. Oh, yeah. So this is gamma I at the kth level is gamma I at the k minus first level. So it's half the size, tensor up. Yes, sorry. Yeah, my mistake. So this is at the kth level, and I'm referring, it's recursive. I'm going to the previous, k. I'm doing this for all even d's, so just go from k inductively to k minus 1. So if I know already 4 by 4 matrices, I make 8 by 8 matrices. If I know 8 by 8 matrices, I make 16 by 16 matrices, and so on. Is this clear? Yes, thanks. Thanks a lot. Those are excellent questions. Yeah. Oh, that's okay. That's next slide. I'm sorry. Okay, this is a matrix, right? And P1 is a scalar. It's just minus P1, the scalar minus P1 times a big matrix gamma 1. Why the minus? Well, I don't know. This is in this paper, right? This is Smita and a bachelor's. Who knows what these physicists are up to, right? But you can see it's like the signature. Right? The signature, this reflects the signature. So why the minus? Beats me, okay? All right. Okay, so those are the momentum space Dirac matrices. Okay, now the relations on our Clifford algebra have some nice consequences. Now, p squared is actually a multiple of the identity matrix, and this is exactly this inner product, the value of this inner product, and this answers your question. Actually, this makes the inner product manifest, right? Because now the inner product is made manifest by squaring a big matrix. Representing the Lorentzian inner product on momentum vectors simply by squaring the matrix P. So one lonely, tiny particle is represented by one big matrix, and then the inner product of this thing with itself is just represented by squaring P. Now the determinant of P, if you work it out, is again the same thing, up to the appropriate even power, and if P is massless, then the determinant is 0. So for massless particles, the momentum space Dirac matrix is nilpotent, this thing is 0, and the rank is half the size. That follows from this. Okay? So for massless particles, this is a way of packaging the inner product and writing the massless condition in a somewhat complicated big matrix kind of way. Very good. Now, Melissa and I never studied Clifford algebras, but we did study Lie algebras, like SON, for example. So how do we get from the Clifford algebra to the Lie algebra? So the Dirac representation, the one we discussed in the last 5 minutes, gives rise to the so-called spin representation of the Lie algebra. So this is little os math frac 1, d minus 1. So the Lie algebra. Let me say a word about Lie groups and Lie algebras. Okay? Lie groups are an object of nonlinear algebra. You pass to the tangent space at the identity, and you get the Lie algebra. Lie algebras are an object of linear algebra. Now, if you are in the nonlinear algebra group, and you will be soon, then to understand nonlinear algebra, you first have to have a very, very good understanding of linear algebra. So the interplay between Lie groups and Lie algebras is just like nonlinear algebra and linear algebra. All right, so this gives a representation. How to see this? Well, if you take the commutator of our two big matrices, gamma j and gamma k, and then for good measure you scale by 1/4, then the resulting big matrices satisfy exactly the relations that the Lie algebra of SO1D1. Okay. Now, once you have a representation of a Lie algebra, that is to say, the linear space, you can get to a representation of the Lie group by applying the exponential map. So if you apply the matrix exponential to these big square matrices, then you get big square matrices, and they form the spin representation of the Lie group, SO, in Roman font. All right, that is the spin representation of the special orthogonal group. That's the one we want to get to, right? We want to get to spinors, and we want to get to the spin representation, but the route to the spin representation is by way of the Clifford algebra. And if everything I say sounds too concrete to you because I told you matrices, try Chevrolet's book. Okay, very good. We haven't gotten to brackets yet. So Marvin is waiting for bra and for cat to make bracket. But we have to do one more thing. We need one more big matrix. Sorry, guys. So we need one more matrix, and there's one more big matrix called C, and that's the so-called charge conjugation matrix. So I've told you what is the spin representation of this Lie algebra. Well, the charge conjugation map matrix describes an equivariant linear map from this representation to its dual representation. Okay? Well, now this is a representation of dimension 2 to the k. The dual has dimension 2 to the k. And this matrix C satisfies the following properties. C times P is minus P transpose C. P is this big matrix that has the entries of momentum vectors linearly for one tiny little particle. And then, in the odd case, there's a minus 1. So, for example, if D is 4, then the charge conjugation matrix is this complex skew-symmetric matrix. If D is 5, it's another complex skew-symmetric matrix. But then if D is 6, it's some other matrix that's now symmetric. Sometimes skew-symmetric, sometimes symmetric, sometimes real, sometimes non-real. So is life. Now, the symmetries of this matrix are quite nice. So C is a symmetric matrix if K is congruent to 0 or 3 mod 4, otherwise skew-symmetric. Now, if K is even, then this is a block matrix, like here. And if K is odd, then it's an anti-block matrix. So block matrix, anti-block matrix. Now, in the block, and the blocks themselves are skew-symmetric. Right? So you can see here this is a symmetric matrix, but the blocks are skew-symmetric. So the blocks are skew-symmetric as K is congruent to 2 or 3 mod 4, and otherwise the blocks are symmetric. Now, these are all elementary statements about square matrices, and everything about these spinors and Dirac algebra is mod 4. Something is true if something is something mod 4. Well, slide 11. I told you this is going to be a hard lecture, and the next lecture will be easier. That's why even if you're not here right now, you can come back tomorrow. Okay, finally, Marvin, the time has come. Bra and cat. So now we have not just one particle, but we have n particles. Now we have n particles in d-dimensional space. And so the ith momentum vector, as before, is coordinates pi1 to pid, the rows of our matrix. And the tuple of these vectors, of course, lies in our variety. Remember, IDN was a prime ideal if d and n is at least 4, and prime is an adjective that means very good. Now, each of these particles now has their own big matrix, has their own momentum space Dirac matrix P sub I, and that's a 2 to the k by 2 to the k matrix, and since we're massless, it has rank 2 to the k minus 1. And now the Clifford relations, right, the defining relation. The Clifford algebra say that the skew commutator of the matrix for the ith particle, pi, and the matrix for the jth particle, pj, well, it's, again, the identity matrix, but just the value of the bilinear form. So the scalar, and remember the value of the bilinear form, those were the Mandelstam variants. If I'm multiplying to take the skew commutator, I take the anti-commutator of two of these big matrices for two particles, I get a big identity matrix times the Mandelstam invariant Sij, and the Mandelstam invariant, I hope, will enter the discussion of Feynman integrals in Lorenzo's talk. All right. Okay, now comes another weird thing. Do not ask me why we're doing this. Okay? What we're going to do is we're going to represent the column space of the matrix Pi. That's a good idea, right? Because the column space is a middle dimensional space. You have a big square matrix, and the rank is half the size. We want to represent the column space. Now what we're going to do is we're going to fill up a bunch of variables up to a quarter of the length. Then we'll do a bunch of zeros, and then more variables for the last length. I'm going to call this vector Zi. This is a vector of unknowns. There's a bunch of unknowns, then zeros, and then more unknowns. And that's a column vector, a long column vector. What we're going to do is we're going to represent this, take this square matrix, Pi. We're multiplying it by the column vector Zi. And the result of this is a long column vector. And this column vector is called bar I bracket. That's Dirac's cat notation. So this symbol is notation for this column vector. Pi times column vector Zi. So this knows about the momenta for the ith particle together with parameters Z that represent the column space. Yes? Do we know that very, very, very good question. Let's hypothesize they are. They are, but I didn't show it. Yes, they are. Excellent question. Okay. Now, once you believe that cat is the column vector, then bra is the row vector. So bra, this other bracket, is the transpose of the previous vector. And these vectors are called spinors. Remember, a spinor is a vector of length 2 to the k, or in this case, 2 to the k. Now these spinors, the bra and the cat, well, they depend on d parameters. So these are the d coordinates of our particle, and all these crazy z unknowns, of which there are to the k minus 1, and together this package now represents the ith particle. All right. Now we take bra and cat, we make bracket. So the spinor brackets of order 2 are the row vector, bra I, times the charge conjugation matrix C, times the column vector, that's cat. Okay? Row vector, matrix, column vector, and that's going to be bracket ij. I know this looks complicated. It's not like everything in life, it's not so bad when you're used to it. Now there's also spinor brackets of higher order, and the spinor brackets of order 3, bracket ijk, is row vector, bra I, Then you take C times Pj, that's the product of two big square matrices of the same size, times column vector cat k, and that makes ijk. And I'm going to stop here. I'm going to only look at spinor brackets of length 2 and length 3. But of course, you could go on. And if you read books on quantum field theory, this goes on. Right? You can look at more spinor brackets. I'm only going to take order 2 and order 3. Right? So here's order L, but I'm not going to talk about it. Now, the spinor brackets are scalars, but of course, there are elements in our ring. Right? They are, what do I mean by this ring? I take the polynomial ring and my p's. I throw in the z's because I introduced these z variables. And of course, I'm modding out by IDN, which was our happy little prime ideal from the beginning of the talk. And the resulting ring I called RDN. And they are invariant under the Lorentzian transformations. So this polynomial ring is generated by ND parameters Pij and these auxiliary parameters Zij. Okay, example. Let's say D is equal to 3. Yes, Mark? The action is actually on the Pi and on the Z. So, okay. Can I tell you? Maybe I spare you. Is that okay? Because I only have half, so I already went on for almost an hour and haven't gotten to the most interesting part yet. So maybe I'll spare you the action, but they're invariant. Okay, so this is how it goes, right? So bracket ij is row vector times, so D equals 3. Row, matrix, 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 column vector, and you have this thing. Remember, because this bra is really this times this, right? And the cat is this times this. The triple bracket, well, it's going to be has degree 3, 2, right? It's cubic in the p's, and it's quadratic in the z's. So those are the things that parameterize our variety. We're now going to be, that's the input now to an implicitization calculation. So from the physics, let's say, we get these things, and what I'm going to be interested in now is what are the varieties that are parameterized by these parameters. What are the relations among order 2 spinor brackets, and what are the relations among order 3 spinor brackets? Very good, let's package them, right? So let me write S for the matrix whose entries are the spinor brackets ij, right? So S is the n by n matrix whose entry in row I and column j is the ij order 2 spinor bracket. And the triple ones, I can think about them as a tensor. So Tij is the jth slice of this tensor. That's an n by n matrix, which are written in this low rank factorization. Okay, now I have varieties. Now I can start. I'm an applied algebraic geometer. A variety just walked into the door, right? It came to me by some crazy parameterization with p's and z's, whatever they are. Now I can begin my work. Now I can say, what is this variety? What is your dimension? What is your degree? What are your equations? And so on. So, yes, please.
These things fall from the sky. For physicists, I wanted to say that for us at least.
I'm so happy. Okay, very good. So, no, very good. I'm of course, I'm exaggerating. Mm-hmm. Okay. So we're now in the session. We already entered the Analara session. What's called communication, math, physics, communication. No, great. I'm just sort of telling my story. I'm telling my story, but of course you're absolutely right. This has very Okay, so what we can say, right? So this n by n matrix has rank at most 2 to the k. It has zeros on the diagonal. So if n is much bigger than 2 to the k, these are actual constraints. And now, whenever you are in this whenever you're in this Dirac business, it depends on mod 4. Okay, so if k is congruent to 0 mod 4, then S is symmetric. Otherwise, it's skew symmetric. Now, the slices of the tensor also have rank at most 2 to the k minus 1. But now the jth row and the jth column is 0. But if D, remember D is 2 times k, more or less. So if D is 1, 2, or 3, or 4 mod 8, then Tj is symmetric, otherwise skew symmetric. These are elementary linear algebra statements. These are elementary statements about linear algebra. To get to nonlinear algebra, well, you have to look at the variety, or you have to apply the exponential map to get you to Lie groups. Okay, and here just spelled out. Now, momentum conservation implies that the sum of these matrices is 0. So Tj is a 2 to the k, is an n by n matrix, n being the number of particles, and these n matrices sum up to the 0 matrix. So this theorem summarizes the linear relations, except for this rank. This essentially summarizes the linear relations among these spinor brackets. Let's just look at this, right? So now we're there, right? So here S looks like this. So now D is 3, so K is 1, and N is 4. So for 4 particles, the order 2 spinor brackets form a skew symmetric matrix. And then there are 24 spinor brackets of order 3, and there are 6 in each of these T1 matrices, so T matrices. So T1 has the first row in column 0, T2 has the second, and so on. And then I'm simply taking the triple spinor brackets with the 1 in the middle is in T1, the 2 in the middle is in T2, the 3 in the middle is T3, and the 4 in the middle is T4. And I'm interested in the varieties in this space. Yes, question? Yes, I think so. Correct? Yes, that can happen. So here that would be 0, but here in the triple situation, no. It's the same particle and can be used twice, can be recycled. Okay, well, that's now, so the talks here are called kinematic varieties. Well, I had these baby varieties at the beginning, the IDN, now let me tell you an adult variety. So an adult variety is the variety of algebraic relations among these spinor brackets. So here we go, right? So this is 4 particles for Flatlanders. So for Flatlanders, D is 3. They have 2 space dimensions and 1 time dimension. So we had 24 plus 6 makes 30 brackets. That defines a 4-dimensional kinematic variety. Now, Lizzie, not only do I like projective space, I actually like products of projective spaces. So here it's quite natural to work in P5 times P22. So these 6 things are homogeneous coordinates on a P5. These 24 things are homogeneous coordinates on a P23. Okay, and now here are some non-linear relations, right? So the ideal is generated by 10 linear forms. These we know already, right? These symmetric matrices sum to 0. But more interestingly, there are 54 quadratic relations. So the one in brown is the Plucker relation, also known as the Schouten identity, and this will come up in pretty much every talk this week. Plucker relation. Now then there are 24 binomial quadrics, like this. They are the 2 by 2 minors of the slices Tj, and then most interesting, there are 29 bilinear relations that link the second order and third order spinor bracket, and this generates the prime ideal. So these relations ensure that the 4 by 5 tensor St, so by this I mean the following. So S is a 4 by 4 matrix. T is a collection of 4 by 4 matrices. If I have 5 4 by 4 matrices, I can package them and make a 4 by 4 by 5 tensor. that tensor, as a tensor, has rank at most 2. And if you do not remember the definition of rank of a tensor, the nonlinear algebra book in yellow and blue comes to your rescue. Right? So a tensor is simply a box filled with numbers, and a box filled with numbers have a rank. Right? So a matrix has rank 1 if it's a column vector times a row vector. In general, the rank of a matrix is the smallest number of rank 1 matrices you need to add to get that matrix. A tensor has rank 1 if it looks like this. Row vector, column vector, and one more vector. Okay? A tensor has rank R if you can write it as R of these, and I will not act it out again. There was a rank 1 tensor. Very good. So they are in the radical. Okay, anyway, there's a bit of a discussion. Radical is another one of those algebra. So here's a general statement. So we're looking at these. So if we just look at the order 2 brackets, there's a theorem. So for d equals 3, for example, so I'm going to write K2dn, the kinematic variety of algebraic relations among the order 2 spinor brackets for n massless particle satisfying momentum conservation in a d-dimensional space. And some familiar words like Grassmannians and secant varieties that fully describe the situation for flatlanders. Now, if you're not a flatlander, then you get, so for flatlanders, just the Grassmannian. For d equals 4 and 5, we also get the 6 by 6 Pfaffian. So we have the first secant variety of the Grassmannian. But then things become more complicated for larger d, and there's a conjecture. Right? So we don't know, in the larger d, there's a precise conjecture what these kinematic varieties are. Now, it turns out for d equals, if d is even, the spin representation. Remember, I defined for you the spin representation. And the spin representation I defined for you by introducing Clifford algebras. The Clifford algebra for the special orthogonal group is the Dirac algebra. From the Dirac algebra, I defined the spin representation of the Lie algebra, and by exponentiation, I went to the spin representation of the Lie group. Now, if d is even, this spin representation breaks into 2 irreducible representations. That's where the other bracket comes in. So physicists have this bracket and that bracket. Because if d is even, such as d equals 4 in the space around us, we need 2 kinds of brackets, one for each irreducible component. Coming up soon, d equals 4. Well, I was hoping that we'd be roughly at minute 20 in the talk now, but I guess we're at minute 65. You know how it goes, right? So, but I'll try to say at least a few words about it. Now, tensor space is nice, right? So I'm going to write K3dn for the kinematic variety. This is now in the space of n by n plus 1 tensor. So I take the order 3 spinor brackets together with the order 2 spinor brackets. And, so these slices are symmetric or skew-symmetric depending on mod 4. I'm going to be interested in the ideal. This is now a variety Lizzie in the product of 2 projective spaces. The first projective space for the order 2 brackets, the second projective space for the order 3 brackets. So there it lives. And here's K, depending whether the slices are symmetric or skew-symmetric. And there's a conjecture. So even for flatlanders, we have a bunch of conjectures. So this variety has dimension 3n minus 8, and Pfaffians and flattenings and so on and so on. So these are familiar words from the applied algebra repertoire. So the upshot is these are very interesting varieties in tensor and matrix spaces, and we know relatively little. For 5 particles, we work this out. So this is K. Upper 3, so 5 particles in a 5-dimensional space-time, and there's a complete description in the paper. This is so upper 3 means I look at order 2 and order 3 spinor brackets. So I have the first projective space just for order 2 spinor brackets, and the second projective space for all the order 3 spinor brackets. And this describes the ideal very explicitly. So K 5, 5 says I have 5 particles, massless in a 5-dimensional space-time, and this is the ideal of all relations. Okay, so with 5 minutes to go, yes, Sandra. This is a very, very small building block. We always see Grassmannians, we see secant varieties, and we see many more things. No, this is, well, there is a relation. So in the most basic cases, you see these building blocks, but then as N and D go up, you see many other things that we don't know yet. So I would say this is an ample area for lots and lots of ways to go, right? And of course, I looked at this from the point of view of a computation algebra person. I think it would be super interesting to go back to talk to people like Lorenzo and others who actually know where this is coming from, and we can discuss what these relations mean. Okay, so this was about the first paper. Now maybe 5 minutes about the second paper. So with Yassin and Anael, we published a paper called Spinor Helicity Varieties in our SIAM journal. And the abstract says that the spinor helicity formalism gives rise to nice subvarieties in the product of 2 Grassmannians. So in this case, in this situation, now D is equal to 4, and we have, therefore, these 2 brackets. We have these 2 different brackets because the spin representation breaks into 2 components. Okay, so let me say just a few words about this. Is the paper. Now, physicists are very familiar with this. They know what lambda and lambda tilde are, and so on, and mathematicians don't. Okay? But let me give you one example that I like a lot. So let's look at 2 skew-symmetric matrices, P and Q. So P is a skew-symmetric matrix in one kind of bracket, and Q is a skew-symmetric matrix in the other kind of bracket. Now, both of these matrices have rank 2. So we're in the product of 2 Grassmannians. But then there's also this additional relation, that's momentum conservation. And now the important quantity in this case is that the Mandelstam invariant, Sij, is bracket ij times the other bracket ij. This relation is the promised unirational parametrization of the Mandelstam variety. Remember this M variety where I said it's difficult to find the parametrization if you're just a lowly algebraist? However, if you come from the history of physics, this is what you do. You form this spinor helicity variety. In this case, it's a special case of a 2-step flag variety, very familiar to Melissa. And you take this 2-step flag variety and then you apply the Hadamard product operation. You multiply one kind of ij bracket by the other ij bracket. And this is a beautiful and somewhat mysterious parametrization of the Mandelstam variety. The general definition in this paper is we're doing K and R. So if nothing in this talk made any sense so far, you can enter now. Let me write GKN for the Grassmannian of k-dimensional vector subspace in an n-dimensional space, soon to be seen in a very positive light by Melissa. I'm going to look at pairs of subspaces V and W such that V meets the orthogonal complement of W in large enough dimension. I'm going to call this the spinor helicity variety. And yes, Lizzie, it's in a product of 2 projective spaces. It's in a usual dot product, let's say. Okay. Now, for example, what is S, H, K, and K? Well, if R is K, then this is 0. and this is void, and it's just a product of two Grassmannians. On the other end of the spectrum, if k is 0, then that's a two-step flag variety, right? So if k is equal to, if r is equal to 0, then this says these two things meet in dimension at most k, and you can see that this is the flags of a k-dimensional space inside an n minus k-dimensional space. Let's suppose that's bigger, inside Cn. So this relation to flag varieties, for example, this has been studied a lot. So there was a nice new paper, or last year paper by Drummond from the physics community with Bossinger from the math community, who really exploited this point of view, Sergio. Now D is 4. No, D is equal to, now D is 4. So the third question is, why do we allow k greater or equal 3? And that's because I like CEGM theory. So CEGM is one of those theories. So this is Cajazzo, Early, and so on. It's a very beautiful theory where you take Grassmannians, not just G2n, but larger. It hasn't really caught on a lot in the physics community, but this setting of spinor helicity variety works really, really, really well in CEGM. R, let's say for you is 0. Except if we go higher, so if in CEGM, R will be k minus 1. In Freddy Cajazzo's theory, the interesting R is k minus 1, but if k minus 2, but if k is 2, then that's 0. Okay, well, there are ideals, there are, distributive lattices and all that, that are very beautiful for the Grassmannian. Let's skip that. As I said, the Mandelstam variables now is the product of these two kind of spinor brackets, and this is a very, very beautiful story. I'm going to end. Yes, don't read it. Let's end. So with minus 10 seconds left, let me just tell you about this picture. So one of the things we do in this program is to look at positive geometry. Now, we don't quite know what positive geometry is. I mean, there's some notion of positive geometries, but whatever it is, whatever positive geometry is, it will incorporate 3 flavors of algebraic geometry. And the 3 flavors are complex. Here's an elliptic curve over the complex numbers. Real geometry, here is an elliptic curve over the real numbers. And tropical geometry, here's an elliptic curve over the tropical numbers. And this is again from the previous paper. So I said that Bossinger, Drummond, and so on looked at this from the point of view of flag varieties. And of course, we want to do this over the real positive numbers. And Melissa will tell you more. Thanks for your attention.